Are there any questions about anything before we start moving on? Just let you know, I wrote half your test over the weekend. So it's a week from Friday. This is kind of a later test than usual. I just decided it's probably a good idea to give you a little bit more time to kind of get going with this whole online thing before I gave you a main test. So that's why this test is a little later than I would normally give in a regular class. I hope you understand. There's no good solution to anything, but that was my best thought, was to spend a little bit more time getting you used to everything, making sure you can do the Proctorio. And I want to mention one more thing about Proctorio. If it did not work for you I think it was last week, the week before, when you had to take those practice Proctorio quizzes, you need to get yourself a computer or get it figured out. Don't wait until the last minute. That doesn't work. For one thing, is the library is not even open at 8:30 in the morning. So last minute won't work. So make sure that between now and next Friday, you have a computer that works with Proctorio. Our library will give you one for free until the end of June. So, you know, you all can get one if you need one. But that's an absolute, don't wait until Thursday night to decide that you need a computer, because it's too late. And I'll have to send an email. It's really easy to the library. They'll give you an appointment to pick one up, pick the computer up. You go pick it up, and it all works. And so far, those who have used the library's computers, they all said it works. So if you had any issues, again, with your own computer, make sure you get a library computer to take next week's test. Any questions about anything? Okay, let's talk about the quiz. And let's get through it. So let me share my screen. Okay, so we have a quiz, and it was find the equation of the tangent plane to f of xy equals 3 minus 2x squared plus xy plus y minus y squared at the point -2, 1. All right, so if we want an equation of tangent plane, what's the first thing we should find? What's the first thing we should find? Yeah, let's find f of xy. And that's not too bad. F of x comma y is equal to, and I'll just write a little out, 3 minus, and then we have 2 times x squared, which is 2 times 4, which is 8. And then we had plus x times y, -2 times 1 is -2. And then we have minus y squared, which is 1. And what is 3 minus 8 plus -2 minus 1?
-8.
Okay, yeah. So it's -8. Notice -2 minus 1 is -3 plus 3 is 0. So you get -8. This quiz had a little arithmetic, not too horrible. Okay. All right, we found f of xy. What's the next thing we need to find? And I'll leave it. F plus x, I think your idea is right. Yeah, f sub x. Good. And let me write instead of f of xy, let's put f of -2, 1, which is what we really found. So now let's find fx. So fx is equal to, and I'm going to do it with xy, and then we'll plug in. So fx is equal to, the 3 goes away, its derivative is 0, minus 2x squared, the derivative with respect to x, is going to be minus 4x. And then we have plus xy. What's the derivative with respect to x of xy? Y. Okay, so plus y. And what's the derivative with respect to x of -y squared? Yeah, 0. So now what we can do is we can plug in. So f sub x of -2, 1 is equal to, and if you plug in -2, you get 8 plus 1 is 9. Everyone okay with that? Okay, we found fx. What do we have to find now? Yeah, now we find f sub y. And f sub y, well, same idea, but now we take the partial derivative of f with respect to y. And to do that, partial with respect to x, with respect to y of 3 is just 0. Of -2x squared is also 0. There's no y. Of xy will be x. And of minus y squared will be minus 2y. So that tells you fy of -2 comma 1 is equal to, and now we just plug in. That's going to be -2. Let me just say it. So -2 minus 2 is -4. Any questions on that? Any questions? Okay, now the next step is to put it into our wonderful formula we have. And hopefully you remember how that formula works. So how does the formula work to find the equation of the tangent plane? Yeah, and it's actually z equals f of x comma y. And I'm going to write x naught comma y naught. Make it yeah, it looks better, comma y naught. And then plus f x and times x minus x naught, and then plus fy times x times y minus y naught. And now plug in. So z equals f of x naught y naught. Well, in this case, f of x naught y naught was -8. And then plus f sub x. F sub x was 9. And then times x minus x naught. That's x minus x naught was -2. So that's a +2. And then plus a f sub y, or -4, times y minus 1. And if you want to clean it up, you can. You can write this as 9x minus 4y minus z is equal to, and we have what, 9 times 2 is 18. 18 minus 8 is 10. 10 plus 4 is 14. Move it over, you get -14. Any questions at all on finding the equation of the tangent plane? Any questions? I do want to give you a little warning, though. This is not a Proctorio quiz, but you definitely want to practice your quizzes without all kinds of notes and stuff like that around and using other tabs on your computer, because next week you don't get any of that stuff. So the quizzes are worth very few points, but if you treat them like the exam, then you'll have better practice. Whereas, you know, if you don't, then you're going to get nailed on the exam. So make sure a couple things. One is you don't have your book or your notes in front of you. Another is you don't go looking on the computer for more stuff. And the third is if your roommates or whatever in your class with you, don't talk to anyone else, because those are going to be requirements next week. So quizzes are good practice, but they're only good practice if you actually do it right. And doing it right is follow the same rules of the exam. Any questions at all on question 1? Okay, let's move on to question 2. And that is, consider the function f of xy equals y times root x. Use the tangent plane at the point 4, 1 to approximate 3.99, comma 1.02. Any questions on the question? Okay, just like we did before, we need to find those 3 things. We need to find f of xy, or f of 4, 1. Okay, and actually I think I need to do this with a equation editor, because we have roots now. F of 4, 1. And again, it was y root x, I believe. Double check. Yeah, it's y root x. So that's going to be 1 times the square root of 4, and that's 2. Any questions so far? Okay. Next, we need to find the partial derivative of f with respect to x. And again, we have y root x. So f sub x is equal to, well, I like to write y root x as y times x to the 1/2. It's easier to think of derivatives. Partial with respect to x is going to be 1/2 times y times x to the negative 1/2. Any questions on the partial derivative with respect to x? So f sub x at our point was 4, 1. So now we have to plug in. So y is 1, x is 4. 4 to the negative 1/2 is a fourth. Sorry, it's a half. A half times a half is a fourth. And I'm going to write this as 0.25, because remember the question had decimals, so it's a little better to have decimals. Any questions so far? Okay, now I do the same thing, but now I do it with y. And we have, again, y root x. So let's do that. So now we have f sub y equals, that's easier because x is a constant, so y times a constant, derivative is a constant, which is the square root of x. So f sub y of 4, 1 is equal to, well, again, it's y root x. Y is, it's root x, and x is 4, so it's just 2. Any questions at all so far? Okay, so now we got to come up with a solution to this. The book used L, so I'm going to use the book's way of doing it. And they're going to say L of xy, or 4, 1. That was equal to, we have a f of 4, 1, which is 2. And then we're supposed to do plus f sub x, which is 0.25, times delta x. Delta x, again, we're approximating 3.99 for our x. or we're using 3.99, and we're coming from 4, and remember it's x minus x dot, and that's 3.99 minus 4, which is negative 0.01. And that's plus. And now what we have to do is do f sub y. F sub y was 2 times delta x, delta y. Delta y is 1.02 minus 1, which is 0.02. Any questions so far? Okay, let's clean this up a little bit. That's 2. That's going to be a minus because it is a negative. 0.25 times 0.01 is 0.0025. And then plus 2 times 0.02 is 0.04. And that is, well, if you go 2 plus 0.04 is 2.04 minus 0.0025, which is 2.0375. And there is our approximation of f of 3.99 comma 1.02. Okay. Any questions at all on that, on part A? So let me write A here.
Would a good way to check our work be to plug 3.99 and 1.02 into the original function?
Absolutely, absolutely. And if you do that, the funny thing is, while you're taking a quiz, I don't know if you know, but I take your quiz also. I just want to make sure that it works and all that. That's exactly what I did. Is I plugged it in, and I'll let you do that. What do you get when you plug it in? And I'm even going to write down the notation for that, so you, because it's something I didn't talk about and I should. So what do you get when you plug it in? Oops, don't do this. Yeah, what do you get? What's your answer when you plug in into the original function? So in other words, you're going to take 1.02 times the square root of 3.99. Probably want a calculator for that. And by the way, on the exam that you'll be taking next week, you're going to be allowed there's going to be a scientific calculator installed only. So that's the kind of stuff you'll be able to plug in. In other words, it can do basic arithmetic. It can do, I think, sines and cosines and roots. Not even sure about sines and cosines, but I think so. So what do you get when you plug in? That's not supposed to be hard. That's a quick little calculator exercise. Probably not very far from 2.0375. I don't see y'all jumping in at once, but it doesn't take very long. All right, 2.0375. That's what you got exactly? I don't think that's exactly right. Because the square root of 3.99 is messy. So maybe some more decimal places. All right, this isn't calculus. I mean, that's not a, you don't need to know calculus to plug in. You need to know basic computers. So it's 1.02 times root 3.99. Maybe I need to do it for all of you. I don't see y'all jumping in. I'm going to use a Google calculator. Yeah, I get 2.0374484. And notice that's very close. It's not exactly the same. 2.037. 4484. So you'll notice that this is accurate to 3 decimal places. Okay, and that's not bad. Okay, that's usually enough for engineers, for example. Not always, but usually that's plenty. So that's one nice thing about the tangent plane approximation. It gives you pretty good accuracy, not perfect. Okay, let's look at part B. These really quick, if you remember how to do it, is now we're supposed to find the differential dz. Well, by definition, what is dz? Okay, yeah, you have the right definition, but even easier is just going to be f of x naught, comma y naught, minus f of minus our approximation. Just going to write APP. So it's how much our error was from what we had before. Okay, so dz is going to be f of x naught y naught, and f of x naught y naught was 2 minus 2.0375. Any questions on that? I think I get backwards, actually. It's the approximation minus the f.
Can you scroll down?
Yep. Yeah, thanks. Yeah, sometimes, again, I see it on my screen, doesn't mean you see it on yours. So let me know if you can't see something. Okay, so we have, it's actually the opposite. So it's 2.0375 minus 2. I hope you don't need a calculator to do that. And that's 0.0375 is our DC. Any questions at all on part B? Okay, so that's the quiz. Tangent planes are important. They happen a lot. They're important for something. It's a hard one because tangent planes, you know, we used it, we approximated something as a tangent plane, but it's much more, there's a much bigger use of tangent planes. Anyone know? The hint is we haven't learned it yet. So it's kind of a tough question, but you might guess. Okay. Turns out next quarter, if you guys take the 202 class, we're going to be looking at the area of a surface and also volumes too. So we're going to have functions of 2 variables, and you want to find out what is the area above some region in the XY plane on a surface. And you're going to find that area by using the tangent plane approximation. And then you're going to take a limit as your delta x and y's go to 0, and then you get the full area. That's next. That's not this quarter. But I want to let you know that it may not feel like we're doing much with tangent planes, and that's because it really is all about next quarter. So it's a tough one, is that we're doing something to get ready for a class that isn't this class. So sorry about that, but that's the way it is. Any questions at all? Okay, let's go and talk about the chain rule. Oops, wrong one. That one. So we want to talk about the chain rule, and I'll show you a couple ways where the chain rule comes up. Sometimes you might have a function. Let's say you have f of xy is equal to, how about xy minus y squared plus 2. But you also have x and y as functions of t. So let's suppose that you have parametric equations for x and y. And let's suppose that x of t is equal to, how about sine of 2t, and y of t is equal to, how about t plus t squared? And what we might be interested in is saying, well, what is the derivative of f with respect to t? So I have a tough question for you. Is this a regular derivative or a partial derivative? Let's write it in words. Is that a regular derivative or a partial derivative? What y'all say? We got definitely do not have agreement in this class. I got partial, regular, neither. Okay, so let's think about it for a bit. Okay, let's think about it. Okay, well, we have this function f, and we're looking at the function f as a function of t. Okay, so this is where I'm in this number 2 thing. So if you look at the function f as a function of t, that means we're starting with the t, which is a single variable. It's not paired with anything. It's just t by itself. And then we're doing some stuff and doing some more stuff and getting a single number. So f with respect to t is actually a function of just one variable. Okay, there's middle stuff, but it's just a function of a single variable. So let me show you for this one. And this could get a little complicated. A lot of people have trouble with this, but we'll do our best. For this one, the notation we should use is not del f, del t, but it should be df over dt. So our big question now is, what is df over dt? And make it bigger because it's way too small. And not del f del t, because f is a function of a single variable. There's just some middle ground stuff. Any questions on that? Okay, now there are 2 ways of going about it. One way is plugging in x and plugging in y, simplifying, and then writing down the answer by taking a derivative. And that works. But it turns out that's usually much harder than the nice way, which is called the chain rule. Okay, so again, we could plug it in. You can write f of x, f of xy is going to be sine of 2t times parentheses t squared plus t squared minus t plus t squared quantity squared plus 2. Simplify that out, find a derivative, and that'll work. But there's an easier way. And this is called the chain rule. And the chain rule, and this is going to be the chain rule, R1 to R2 to R1. So let me just copy that. Okay, so when we have a composition of functions, so we have a f of xy, and we also have x of ty of t, then we can find the derivative as follows. And let's write this out. And it turns out that d, let's get that d fraction, df over dt is equal to, well, the idea here is a chain rule. So you kind of want to say, remember the chain rule in regular variables was like df over dx times dx dt. What's the problem with that? I want to add one more item to number 5, actually, implicit. What's the problem with just saying it's df over dx times dx over dt? I'll even write that out, and we'll see there's going to be a problem. There's 2 problems, it turns out. So anyone see any issues? Right? Because you could say, hey, the dx's cancel and you get df dt. Okay, there's no x. Well, look at my example. The example has x's, has an xy plus y squared plus 2. There's an x. And we have x of t is sine of 2t. But there's 2 problems. Anyone see the 2 problems? One is actually pretty obvious. Doesn't mean that's the one you'll be looking at, but okay, you found the one that's not obvious. One is we ignore, you can't just ignore the y. That just feels wrong, doesn't it? Okay, another one is there is no such thing as df over dx. So that one I could fix immediately without any thinking. Is I can take that df dx and I can change that one to del f over del x. That's an easy fix. But then I can't just ignore the y. So it turns out, if I want to really make this equal, I need the y also. And the way the chain will work is it's a sum. And that's the chain rule. It says that if you have a function that goes from t to xy, and then another function that goes from xy to real numbers, and you want to find the partial derivative of the composition of that those functions, the derivative of the composition of those functions, then df dt equals del f del x times dx dt plus del f del y times dy dt. Any questions on the chain rule? Okay, what I decided not to do is I'm not going to prove it. There is a proof in the book. It's kind of messy, and I didn't want to spend like half the time today just doing the mess. But you're welcome to look at the proof. And I don't think it even does all the chain rules. It just does one of them. and it's doable, but you won't be responsible for the proof. But I'll be happy to chat with you in office hours if you want to read through the proof. That's just a note. Instead, what you need to do is you need to do two things. One is familiarize yourself with the formula, and the other is to be able to use the formula to find derivatives. Let's do our example. So for our example, we have f of xy is xy minus y squared plus 2. We have x of t is sine of 2t, and y of t is t plus t squared. And we want df dt. Okay, so let's do it. So df over dt it always makes it way too small. About 18, that's better. So df dt is equal to, well, del f del x. What's del f del x? Nice and easy. Yeah, it's just y times dx dt. What's dx dt? Yeah, it's just 2 cosine 2t. That's a chain rule, by the way, for regular old functions. 2 cosine, which you're still responsible for, by the way, cosine of 2t. Any questions so far? Okay, and then del f del y. What's del f del y? For example, yeah, it's x minus 2y. And then times dy dt. And what's dy dt? Yeah, 1 plus 2t. And there it is. Now it looks a little weird. Sometimes you want to turn everything into t's, and then you just substitute where you see an x, you put sine 2x, and where you see a y, you put t plus t squared. If you care about having everything in terms of t. If you don't, then this is fine. Any questions at all about this example? Just a note, what if we wanted to find? Let's find del f del t. Or df dt at t equals t equals 0. Okay. So to do that, and this is why you don't have to do all the substitution at the beginning. It's easier to deal with the numbers first. So what we can do is we're going to plug in 0 into everything. So first thing, what is x of 0? What's x of 0? Okay, so x of 0 is a sine of 2 times 0. And that's the sign of 0, and the sign of 0 is 0. What is y of 0? That's 0 also. So, and by the way, Now we plug in, we know x is 0, we know y is 0, and t is 0. And what do you get for del f del t at 0? It's 0. Okay, so del f del t, let's write it this way. At 0 equals 0, and we're done. So notice in this case, you definitely don't want to do the full substitution and simplify and all that stuff. If all you care about is what's the derivative at 0, you just plug in everything. And it only takes a couple seconds and you're done. So I did want to show you an example where you don't have to waste your time in doing all the plugging ins for the functions. Any questions at all on this chain rule example? Okay. So this is a chain rule from R1 to R2 to R1. Okay. So by the way, it doesn't make any sense to say, what is the chain rule for functions of more than one variable? Because there's lots of chain rules. Okay. But the good news is once you see a couple of them, then you understand what's going on and you can make up any others you want. So let's do another one. So let's go back to our list. Let's do R2 to R2 to R1. Get to that 7. Doesn't want to go away. There it is. Okay, so we want to go from R2 to R2 to R1. And so let me explain how that works. And the idea is once you understand the chain rule that we did before, this one's going to look very similar. And that is, let f of xy be a function. And I'll even call it z, just for fun, equals f of x comma y. That way you can see why it goes to R1, because z is like the R1, one variable. And let's suppose that x of u comma v is, and we have y of uv. Are differential functions. None of this works. If you can't take a derivative, you can't even talk about the chain rule. So I didn't mention that in the last one, but obviously, if you can't take a derivative, then it doesn't make sense to say what is a derivative. Do y'all agree with that? Okay, so let's suppose we have differential functions. So now what you can say is that we're starting with uv. Those get sent into R2 by x of uv and y of uv. And that gets sent into R1 by z equals f of xy. So what we want is, how do we find the partial derivative of f with respect to u, for example? Okay, and the idea is if we look at what the chain rule said before, where we had del f del x dx del dt plus del f del y dy dt, it's really similar. Any guess on what this might be? The first thing, everything will be a del because we don't have a function of one variable at all here. So I'm just going to write del because I know it's got to start there. And you want to think of it as fractions. Any guess on what the first fraction is going to be? I don't see y'all jumping in, but hopefully you can tell me. Del f over del x. Good. Perfect. Del f over del x. But then we have to multiply it by another fraction. What fraction are we going to multiply it by? Definitely going to have a del, because all we got is dels here, because there's just everything's of multiple variables. There's no single variable by itself. And that's going to be del f del x times not times del f del y. So we want some cancellation. It's going to be del x over del u. And that way, if you look at that, the del x's cancel and you get del f del u. And that's a good thing. Do y'all agree? Okay, but we can't just ignore the y. So then what we're going to have to do, and I'm going to do the same thing with the y and put a plus in between, just like we did before with the chain rule. And we're going to have del f del y times del y del u. And I want to make it bigger. A little too big. And red, because it's an important one. So this is a chain rule when you have a two variable function to a two variable function to one variable. Any questions at all on this example? Not example, but this chain rule, I guess. Notice it's a different chain rule than the last one, but it's the same feel, isn't it? Okay, so let me talk about when you use it. Let's use this. And I'm going to do it by example. And it's kind of the most important example there is. So let's suppose, oops, too big. The f of xy was equal to, keep it somewhat simple. How about y over x? Actually, it doesn't do it automatically. I got to do fraction. Plus xy. How about x squared? A little better example. Find this is just going to be thrown at you unexpectedly, but we got to do it. del F over del R. Any questions on the question? Notice that I didn't give you what X and Y are in terms of R in terms of X and Y, or any of that. But that's something you're supposed to all know. This is really important. When you have maybe a physical property and you have it in X and Y's, and you want to find out what is a change in the function as the radius expands, as you go farther and farther from the source, then that's going to be something that you're going to be doing with the chain rule. So I'm going to give you a minute or so. I want to see if you can do this. So if you can find del F over del R. Again, I think it's important for you to try it yourself instead of just watch me the whole time. And that way you get to practice, see if you get it, and then I'll do it and see if you got it or not. And this brings together a few sections, which is good. And by the way, this is done all the time in physics and engineering. I'm just going to give you a minute or two. Shouldn't take more than 2 minutes, so. Okay, what'd you get? See if you can say it or put in the chat box. Probably chat box easier because it's more of that kind of thing, more of a typing thing. What'd you get? I don't see y'all typing in, but maybe you are. All right, maybe you got stuck. I'm not sure. It's hard to tell. One thing with the online is I can't read your thoughts here. Can't look at your faces and say, hey, I was really confused when you don't pull your video up. Or I can't walk around the room and watch. Okay, so the first thing is we need to understand what X and Y are in terms of R and theta. And hopefully you remember that because that was really important. And we had a whole section basically on that. So let's pop that in. So first thing is x of r theta was equal to r times the cosine of theta. We've used that a lot already. And y of r theta was equal to r times the sine of theta. Okay, so now what we can do is we can work out, and I'm just going to copy and paste because it's easier to do it that way. And then I can substitute in as I go. I don't want it to be red though. Okay. There we go. So now we can say del f del r is equal to del f del x times del x del r plus del f del y times del y del r. Oops. Del y del r. Any questions on that so far? Just taking the chain rule and then adjusting the letter. It's r instead of u. Okay, that is equal to, and now we can have del f del x. So you go to the original function, f is y over x plus x squared, take it with respect to x, and we get negative and then a fraction, y over x squared, and then plus 2x. And I probably want that in parentheses. And then times del x del r. And del x del r now, if x of r theta is r cosine theta, del x del r is cosine theta.
Can you scroll down a little bit?
Sure.
Thank you.
Okay, so there's our first piece, and then we go plus, and we have del y, f del y, and it's up a little bit y. There we go. That's an easier one. That's just going to be 1 over x. Times del y del theta, del y del r, which is sine of theta. And that's it. Any questions? Any questions on this solution? There's not too much to do if you know what to do. Okay, sometimes you want to substitute y and x in terms of r and theta. Sometimes you don't. Depends what you're doing with it. So I'm just going to leave it like this. But substitution, hopefully y'all know how to substitute. Any questions on the idea of having a function of x and y and looking to see what the partial derivative of that function is with respect to, say, r? I could have just as easily done theta, but I chose r.
I do have a question.
Sure.
How do you know, or no, not that. So what is the difference between the two functions in which you're using the different types of chain rules? Like what made it, what about this function goes with the certain chain rule that you use?
So how do I know that? So like if you look at the last example and this example, you mean? How do you compare the chain rules?
Yes.
So it has to do with how many variables there are. So you'll notice that when you have polar coordinates, we have x as a function of 2 variables, r and theta. Do you see that? And
Yes.
y is also a function of two variables, r and theta. Whereas in the last example, we had x as a function of just a single variable, t. You see that?
Yeah.
So that's why the first example starts at R1 because that's your t. The second example starts at R2 because it's r and theta. There's two variables. Any questions
Okay.
on that? Okay. And there's lots of chain rules. I think I can do the fifth one next. There's nothing too special about the fourth. Well, maybe I'll do the fourth one. But I'm gonna do it kind of quickly because it's just kind of, you do it again. And I'm just gonna like make up the chain rule because hopefully by now you get the idea. So let's suppose instead, now we're gonna have let's suppose f of, let's see if I want to do it that one. Just a minute. I don't remember. We're going 3, 2, 1. So f of xy is equal to, how about x minus 2xy? And let's suppose that x of u comma v comma w is equal to, yeah, I can do this one, is equal to, how about u minus w? And y of u comma v comma w is equal to, how about how about vw? Oops. It's taking too much space. There we go. So you can do the same idea, and now you could say, what is the partial derivative of f with respect to w? Well, does it matter if there's 3 variables? Not really, does it? So what we can do is we're going to take the partial derivative of f with respect to x, which is just 1 minus 2y. And then times the partial derivative of x with respect to w. And that's just going to be -1. And then we're going to go plus the partial derivative of f with respect to y, which is -2x, times the partial derivative of y with respect to w, which is v. And that's it. So if there's 3 variables, no big deal. Do you all agree? We can also do the other type of 3 variable and 2 variable, and that's in backwards. So let's suppose we have f of x, y, z. And let's suppose that was equal to, how about yz minus 4x. And how about I don't know, how about a single variable? How about let's say x of t equals t squared. Y of t is equal to 3t, and z of t is equal to, how about e to the t? And we can say find del f, oh, sorry, not del f, df over dt. Now, I haven't done one of these yet, but my guess is you could figure it out now that we've kind of seen a bunch of chain rules. So let's do it in symbols first. df dt is going to be equal to del f over del x times dx dt. And then we have plus, and we do the same thing with y and z. Del f del y. Oops. Times dy dt. And then plus del f del z times dz dt. Any questions on this chain rule? Notice t is a single variable. It doesn't have any partners, so that's why it's a d instead of a del. And you just do it. It's not that hard. Hopefully you agree. So what we get is del f del x is going to be just -4 times dx dt, which is times 2t, plus, and then we're going to have del f del y, which is just z, times dy dt, which is times 3.
Can you scroll up?
Yep.
Thank you.
Times 3. Okay, and then plus del f del z, which is e to the t. Wait, sorry, del f del z is, no, sorry, it's y times e to the t. And there's the FTT. So it's fine if there's 3 variables, you just put more pluses in. If there's 10 variables, you'd have a whole lot of pluses. Any questions on the idea of the chain rule? Okay. The chain rule, by the way, let's suppose we could have, say, let's say x. Let's say we have f of x comma y is equal to x minus 3y, just making something up. Let's suppose that x of x is equal to r cosine theta. Standard polars. And y equals r sine theta. But then we could also have r of t is equal to 3t, for example, and theta of t equals 5t. And we could ask for what is derivative f with respect to t. And we could say, what is df dt? And then you can say df dt is df dx times dx dr. And that's going to be a del x del r. Plus del f del y times del y del. Actually, let's go we want dx. We do want dx dt. So let's get this right. So we can say that's true. Do you agree? Oh, that should be a t. Okay, that's true for the chain rule, right? But then we could take this further. And what we can say is we can say, well, what about dx dt? Well, to find dx dt, I can use the chain rule. And I could say dx dt is now going to be dx, actually del x, over del r times dr dt and then plus del x del theta times d theta dt. And then I could do the same idea with dy dt. I can get rid of the dy dt and write that in terms of r and theta. And I'm going to do a copy and paste. Hopefully it'll let me. Yeah. And just change the x's to y's. Okay, and that's a chain rule also. And I'm going to let you, it's a lot of kind of messy, but you just plug it in at that point. I'm going to let you plug it in. It takes too long to plug it in. You've got it. But you just plug in. D theta dt, for example, is 5. Dr dt is 3. And you know dx dr dx d theta. So you can do all of that. And you just plug in. Okay, so it gets messy. When you have the chain rule and you have multiple steps, it just gets really messy. And there it is. Okay, the very last thing I want to do is implicit differentiation. So let's suppose we had something like this. Let's suppose we had, say, x, y, z squared plus x, y squared minus z to the fourth plus 3 equals 0. And I want to find out what is the partial derivative of z with respect to x. Any questions on the question? Any questions on the question? Okay, what I don't want to do is solve for z and then take partial derivatives. That'd be miserable. Do y'all agree? I could do it, but it'd be really horribly messy. So what I want to do is I want to implicitly differentiate. And that's the key to solving this, is you use implicit differentiation. So what I'm going to do is I'm just going to write down blindly del z del x. And what I can say is I have this function equals 0, right? The left-hand side equals 0. Any questions on that? And we want to find dz dx, and we don't know that. So I'm going to just say, well, maybe I can take a derivative implicitly. And I'm going to go del f del x is equal to del f del z times del z del x. That doesn't quite work. What's wrong with that? What's the problem with that? Problem is I have to use a chain rule. I don't have much time, so let me just finish it off quickly. So it's going to be del f del z del x plus del f del y del x. And then plus del f del x plus, whoops, times, I want the plus there. And then I'm going to have del f del x times del x del x. What's del x del x? Hope you can all tell me. It's very easy. Yeah, that's just 1. Okay, so what's going to happen is we can say del f del x now. We know del x is 1, right? So things kind of work out nicely. I'm kind of out of time. come to the finish line using their notation. So here is the punchline. And that is that del z del x is equal to negative make it a fraction, make it del. It takes forever to type these things. Sorry, that's why it's taken a while. Del z over del x is equal to negative, and then fraction, yep. And it's going to be del f over del x over del f del z. So this allows us to do implicit differentiation. So what we do is we take the derivative of f with respect to x, divide it by the derivative of f with respect to z, and that'll give you the derivative of z with respect to x. So if we have our original, pop that in again. Well, del f, we're going to have negative. So to write this and that. And then we just plug in. So del f del x, start there. Del f del x is just going to be yz squared plus y squared. Del f del z will be 2xyz minus 4z cubed. And there's our derivative of x of z with respect to x. And that's called implicit differentiation. Sometimes you have numbers to plug in, and you plug in and you're done. But sorry, I went a little longer than I usually do. But it's hard to like stop. Stop the share and stop.